Hi, I'm Neha Rungta. Welcome to this session. I am a scientist in AWS, and today I'm going to talk to you about provable security. So, I will start by telling you what is provable security, how AWS is using it, and how you can use it too. So, customers wonder, how does AWS maintain security at scale? What is AWS doing to keep my data secure? What should I be doing? And there are many ways that AWS helps you here through security resources, tools, services, and expert guidance. Today, I'm very excited to tell you about an area we're pushing the boundaries, inventing the future. It's called automated reasoning. It provides the highest level of assurance with provable security. So, what is it? What is provable security? It's the use of mathematical logic to prove the desired security properties hold of your system. So let's unpack that a little bit. Mathematical logic is an application of formal logic to math. It was used to develop axiomatic frameworks for geometry, arithmetic, and analysis. It allows us to make rigorous but finite arguments about potentially infinite structures. So let's look at an example. This is Euclid, a mathematician in 300 BC. He proved the Pythagorean theorem, which states that the square of the side opposite the right angled triangle is equal to the sum of the square of the other two sides. Now, how did Euclid go about approaching the reasoning about these triangles? Did he try to fuzz the triangles? Did he try to audit all the triangles he knew about? Did he have an AppSec review process for triangles and reject the ones that didn't satisfy his threat model, hypothesis? Or did he analyze all of the logs of all of the triangles that he knew about? Spoiler alert, no, he did not. He used symbols in geometry to represent many concrete triangles and many concrete values and to prove that the theorem holds. The process wasn't automated, but the reasoning about the proof held for all possible triangles, infinite triangles, without ever having to observe all the triangles. And the use of algorithms to find and audit the proofs led to automating the manual reasoning. In essence, automated reasoning is a way to get comprehensive visibility into the security of a system. Automated reasoning uses the rules about a system to logically infer its future behaviors. It doesn't try to look at historical data to predict an answer. Instead, it analyzes models of systems to prove its correctness. It looks to say what the systems might do, what they will do, and what they will never do. And where has it been used? In a variety of applications. In hardware verification, to prove the correctness of the ALU design. In my previous life, in my previous job at NASA Ames, I worked on the verification of collision avoidance systems. And I also worked on verification of unmanned spacecraft, medical devices such as infusion pumps, and now the cloud. So we all know computers aren't built out of triangles. Modern computing is a bunch of zeros and ones. Even the most complicated systems are simply zeros and ones. In the cloud, we want to prove properties of programs, protocols, networks, and policies. And automated reasoning provides us an axiomatic framework for considering all possible executions in the program, all possible requests in access control policies, and all possible configurations for networks. Now, this is very similar to what Euclid did. We are looking to use automated reasoning. We are looking to use symbols to make finite arguments about the infinite. So where do we start? Let's start by answering, how does AWS keep my data secure? There are numerous foundational systems in AWS, such as custom hypervisor, encryption code, bootloaders, and even an IoT operating system. We leverage automated reasoning to prove the correctness of these foundational low-level based systems. Now, we use testing to validate code against a concrete set of inputs. And at AWS, we raise the security posture of these foundational systems through formal proofs that provides the assurance that the code is both secure and correct for all possible program inputs, and allows us to prove that the code is free of memory errors, infinite loops, or any undefined behaviors. So to get started on this, we have developers who start from the source code, and then they can also specify a security property in the same way they would write a test harness. You can call that, say, a proof harness. In a test harness, what you do is provide concrete values for your test, while in a proof harness, you provide symbolic values for those same inputs. And this goes into your proof tools that symbolically analyzes all possible paths in your C program with all possible inputs symbolically and gives you a result. If the proof fails, we get a counterexample and a test case, which explains an instance of why it failed, or it provides you a successful proof. Now, the key here is that the developers write these security properties or a proof harness as part of their regular development workflow. It allows them to keep their proof harnesses updated and maintained as the system evolves. One of the examples that we've used it in is FreeRTOS. So FreeRTOS is an open source, real-time operating system for microcontrollers that make small, low-power edge devices easy to program, deploy, secure, connect, and manage. And the FreeRTOS operating system was downloaded once, like every 170 seconds last year. And we have proofs of memory safety, thread safety, and functional correctness. One example is the FreeRTOS concurrent queue implementation, and its correctness proof allows us a higher level assurance of the correctness of the FreeRTOS inter-process communication, which uses this data structure. These proofs are publicly available and are run as part of the continuous integration to help ensure their continued maintenance. I want to talk about another example of a foundational library. It's the S2N BigNum library. BigNum libraries are used for high precision integer arithmetic. Say that's around about 1,000 bits. Most asymmetric public-private key crypto systems like RSA use these BigNum libraries. It's also used in S2N. S2N is an Amazon implementation of the TLS SSL protocols that is designed to be simple, small, fast, and with security as a priority. The proof, which is also available on GitHub, has formally verified correctness of all the operations of this library. And there's also a proof that it's free of side channel attacks. As we move up the stack to consider how are we leveraging automated reasoning in AWS to make sure that your workloads and data is secure in the cloud, protocols, and one of the key pillars to security is encryption. KMS is an AWS managed service that allows you to manage cryptographic keys and control its use. And we have protocols for KMS. Protocol verification has been widely leveraged in hardware to ensure correctness. And we are applying and extending similar verification techniques to ensure that our crypto protocols that describe how customer data is handled in transit and rest is done correctly and securely. So this picture should look familiar as it's similar to the one that we saw for the foundational C code verification. But here, instead of source code, and we have a formal model of the protocol, and we also have a proof script. Now, this is done by subject matter experts or proof engineers, and it goes as input to the reasoning engines. And similar to analyzing all possible code paths, it analyzes all possible paths through the protocol. And if the proof fails, you get a trace. But if the proof succeeds, you can now independently check whether the proof was is correct or not. We have a published peer-reviewed technical paper that presents the machine check proof we have that the cryptographic keys protecting customer keys are maintained securely across all AWS servers. And the connection of code to protocol is checked continuously. You can download the protocol description and the proofs, which are open source, and you can independently verify their correctness. Now, to close the loop, we went one step further. We want to also ensure that all internal services that handle customer data use these crypto APIs correctly and securely. For that, we do proofs of the service code to ensure that all customer data is encrypted before it is stored, logged, or passed to another service. I talked earlier about exploring infinite paths to the program. The analysis here tracks the data across all possible paths through the service code to ensure all customer data at rest is encrypted. This exploration of all paths, infinite paths, and doing it symbolically is at the root of scaling provable security and root at how we are leveraging provable security to keep your data secure in the cloud. Switching gears to how you can use automated reasoning, I'm going to talk about two automated reasoning engines used for the analysis of how you can use for the analysis of your networks and policies. So let's start with networks. Amazon VPC is a virtual network that closely resembles a traditional network that you'd operate in your own data center, with the benefits of using the scalable infrastructure of AWS. Now, if you want to build a web application, you have to first build some web servers. These web servers will likely talk to application servers that do all of the interesting computation based on the data contained in the data servers. All of these servers will have IP addresses, so they can talk to each other. And then you will have to route traffic from the internet to the web server so your customers can use your application. Now, however, with this configuration, the internet can send traffic to all of these servers. So what you really want to build is a minimal interface to the internet so that the customers can only need to interact with the part of the service that they need to. To do this, you can first put all of your servers in what we call a virtual private cloud, or VPC. You can think of a VPC as a virtual version of a data center. Within a VPC, we can put each tier of your application in its own subnet. You can then lock down the interfaces of these instances of these subnets using firewalls, or what we call security groups. That way, the servers in your VPC can only talk to the servers that they need to talk to complete their specific task. Finally, you can give publicly routable IP addresses to the web servers and set up routes from these servers to the internet so your customers can use your application. Now, how can you determine whether or not that the network you've built actually reflects the original security or compliance requirements that you intended? How can you track the state of your network through these changes? We built a service called Tiros that allows you to translate the control plane configuration of all your VPC constructs into mathematical constraints that can be understood by a reasoning engine that is called an SMT solver. Now, all you need to do is simply ask the SMT solver any question that you have of your network. Here's an example. Can someone SSH from the internet to instance A? And the SMT solver comes back with an answer showing a path from the internet to instance A via port 22, the port associated with SSH traffic. You can use this feature in two generally available AWS services, Amazon Inspector and the VPC Reachability Analyzer. Amazon Inspector lets customers like you set up periodic assessments of your networks and produce findings that indicate whether you have EC2 instances that are reachable from the internet and how. While the VPC Reachability Analyzer is primarily used to debug connectivity issues. You can specify two endpoints, and VPC Reachability Analyzer will let you know what paths exist between these endpoints and why no paths exist between two endpoints. Now, similar to networks, you can also leverage automated reasoning to analyze your policies. IAM is a service and also a policy language that allows you to control access to your resources within IAM or across all of AWS. AWS is a collection of resources, and the policy provides a means to share access between the resources or between users in your account and resources, and or across different accounts, different organizations. The question you may have is, did I grant the permissions I intended? This is similar to the ones, did I build the network that I intended? So what would be a question to ask here? A question here is, what is shared outside an account? Now, you have four accounts here, XYZ, you have website, you have ABC, and you have the audit account. For that, we need to answer, what are the accesses that cross the boundary? Now, let's look at these accesses. You have the website account that has access to the API gateway. Now, that sounds reasonable because a website might want to connect to the API gateway. You have an audit account that connects to an S3 bucket. That also seems intended, so I'm okay with that. But this access from account ABC to my KMS key, that seems fishy. And I determined that this external account access to my cryptographic key is unintended, and I want to remove it. So now that I have the visibility and answer to that, I can remove it. So AWS Access Analyzer uses automated reasoning, and you can use it today to determine all possible access paths allowed by your resource policies. Access Analyzer helps you identify resources in your organization and accounts, such as S3 buckets, Lambda functions, IAM roles, KMS keys, SQSQ, secrets from Secrets Manager, and tell you which of those are shared with an external entity. It lets you identify unintended access to your resource and provides you an ability to help remediate it. For every instance of a resource that is shared outside your account, Access Analyzer generates a finding. And findings include information about what type of access and who the external entity is that access is shared with. And you can review each of these findings individually to determine if the access is intended and safe. Then you can just archive that finding. Or if the access is unintended, you can go to the respective service, edit the policy, and Access Analyzer will continuously run based on the change, and the findings will go away. You can go turn on Access Analyzer now. It's available at no charge, and it will provide you a visibility into sharing and allow you to remediate any unintended resources that are shared. Now, what's possible under the hood? How does it actually, what's the secret sauce? What's the ingredients to the secret sauce? And that Access Analyzer uses a policy engine called Zelkova. Here's how Zelkova works at a high level. The inputs to Zelkova are a policy and a question. The input are different types of policies: the identity policy, role trust policy. And then we also have the question. What are the different questions? Can Jane launch EC2 instances? Can anyone outside my account 123 assume this role? Is my bucket accessible outside the VPC? And again, the reasoning of this is encoded in math, in logic, And that allows us to answer these questions. What makes Zelkova special is it doesn't look at just some requests. It looks at all possible requests. Of the millions, of the billions of possibilities, it looks at every one of them. Now, it sounds like science fiction. It sounds impossible. And this is why we need to apply automated reasoning. We don't question that the Pythagorean theorem reasons about billions and billions of infinite triangles. It's the same here. In addition to Access Analyzer, there are other features and use cases that Zelkova is driving. Let's look at them. It allows you to be secure by default. We built block public access using Zelkova. We want everyone, except people who are doing web-based assets that they need for their application, except those people, everyone should have block public access. You can do it for existing buckets as well. You can go through all your buckets that are not intended to allow public access and enable that option. You can enable BPA at the bucket level. You can also enable BPA at the account level. The reason for that is when you turn on block public access for your account, you're locking down public access for every S3 resource, object, and bucket now and in the future. This is incredibly powerful. It is future proofing. Any S3 resource created in that account will not be public in any time in the future. Seesawing back to another use case, I'll talk a little bit about how we use Zelkova internally. It's used by our internal AppSec team. Now, this team has a broad security charter of keeping AWS services secure. They're responsible for guiding the developers, helping create a decision support system and providing visibility for security experts, and also initiating a rapid response when necessary. So coming to S3 buckets, like our customers, our own services use S3 buckets. And the AppSec team has been able to leverage Zelkova to do a comprehensive analysis of all the policies. It can detect and remediate policies with broad permissions. Here's an interesting point. The scale of AppSec means that we can't afford many false positives, because if the AppSec tooling detects a policy in a service with broad permissions, it automatically cuts a high severity ticket to that team, and the on-call engineer gets paged by it. They get up and they review the ticket and make the appropriate fixes. Now, if the tool provided false positives, this would not work in the current workflow. So in addition to the automated reasoning tool covering all possible scenarios, it also has to ensure that the false positive is very low. And the team also applies this process early and often. It starts from the design and coding phase, because infrastructure as code means that we can review policy changes like any other code changes. The pre-launch security review, where you can evaluate it in like pre-prod environments, and as well as you can monitor it continuously and raise alarms when the policy deviates. I want to end on an application that most of you will be familiar with: the payment system on Amazon.com. Last year on Amazon.com, we sold over $386 billion worth of product to our customers. One of the things that requires is that the ability to safely and securely store critical payment information for our customers. We want customers to trust us when they enter their data into one of these forms, and we want to continually earn and maintain that trust. At Amazon, we are building a secure payment vault using AWS, and we are using Provable security to verify it. To look a little under the hood, at the root in AWS is an API call. It's the ability of a principal to request AWS to perform an action on a resource. And to make sure that the API calls are secure, we break down the anatomy of this API call. It starts with the application code making the request. The request must be allowed by the organization policies that apply to the AWS account. And we must have IAM permissions attached to the principal and resource. And finally, we have the network, that the request actually has to get from the principal to AWS over the network. Now, in order to secure our payment wall, each of these teams have built separate automated reasoning engines for the application, for the organization team, for the IAM team, and for the networking team. So there are separate automated reasoning teams working on separate automated reasoning products for each of these layers. But we also have an automated reasoning team who's using the combination of these tools that I've shown you in this talk to verify our secure payment wall. And this allows us to maintain and verify that the customer trust in us is well placed. If you're interested and want to learn more, we have an AWS security webpage with many of the details. We have blog posts describing specific features and tools. We also have talks by our customers on how they're leveraging some of our automated reasoning capabilities to help them stay secure. We have talks from Goldman Sachs, LogMeIn, and as well as Bridgewater Associates. We have peer-reviewed scientific papers on the how. You can go download them and read them. And we also have podcast interviews with leading scientific figures. And as we keep launching new capabilities and features, this is a place where you can keep up with what's the latest in provable security. Thank you very much for your time. I hope you enjoyed this session. We look forward to hearing your feedback. We always love hearing feedback, so please complete the session survey. Thank you again.
You've heard of MongoDB, but have you heard that MongoDB Cloud goes beyond the database with services like full text search, data lake, mobile support, and data visualization? Visit mongodb.com/cloud to learn more.